Alright, so in this video I wanted to prove quite a remarkable result in mathematics, namely that if a and b are positive real numbers, so then if I put a1 equal to the arithmetic mean of a and b, and b1 is equal to the geometric mean of a and b, and if I recursively define a sequence, two sequences like this, so that each a is the arithmetic mean of the previous a and bn is the geometric mean of the previous a's and b's, then well, firstly, this an and bn converge to the same limit, which is quite easy to prove, and we will do this in this video. And but what's more remarkable is that if we denote this common limit by m, actually this limit is called the arithmetic-geometric mean of a and b, then you actually have this result, which is 1 over m is equal to the integral from 0 to 1 of this a squared cos squared plus b squared sine squared theta. And actually that's 2 pi. And that's objectively quite remarkable, because a and b can be absolutely any positive real numbers whatsoever. Actually, I missed 2 over pi here. Sorry, yeah. And actually, that's not 2 pi, that's pi over 2. Right. So now we are going to prove this result in this video. And I'll start by showing that this limit actually exists and is equal in both sequences. And to do this, so let me erase everything. To do this, we need the famous arithmetic, well, it's better known as the AMGM inequality. And this states that a plus b over 2 is greater than root of ab if a and b are positive real numbers. And I've put strict equality here because we have strict equality here. And now we are going to show that so this can be written as a1 is greater than b2. And so if we have a real number line here, so b is somewhere here, we are assuming that b is smaller than a without any loss of generality, then the arithmetic mean lies straight in the middle, and the geometric mean is slightly less. This diagram is not to scale, of course. And if we repeat this process, we'll have the arithmetic mean of a1 and b1 right in the middle, and the geometric mean will be somewhere here. The means are always contained between the two numbers used to calculate them. And so what you notice here is that we have one interval here, and nested inside that interval is another interval, and nested inside that interval is yet another interval. And so this sequence of intervals AB, A1, B1, A2, B2, and so on, is a sequence of nested intervals of constantly decreasing length. And we know that to every infinitely nested set of intervals with length decreasing towards 0, there corresponds one and only one real number. And so these bn's here, they converge to a limit, and these an's here, they converge to a limit, and these limits are exactly the same. So we'll call this limit m. M is a real number, so the limit as n goes to infinity of bn is equal to that as n goes to infinity of an, and we'll call that m. So now we've shown one thing, and we are going to show something else now, in order to prove the result which we want. So I'm going to prove right now that if you take this integral which we are interested in, so a squared times cos squared theta plus b squared times sine squared theta, if you take this integral here, then it's actually equal to the same integral, but if you replace a and b by the arithmetic means and the geometric means. Right, so that's what we are going to prove first, and that's a key step in proving the result which we want. So let's go on to the proof. So to do this, first I'm going to recall the elliptic integral of the first kind, and it's defined like that. So k is called the modulus, and it lies between 0 and 1. And the elliptic integral of the first kind, that's just a summary of previous videos. So for full proofs, you can look at the previous videos. So that's how the elliptic integral of the first kind is defined. And if you do an easy substitution, if you put x equals sine of theta, you see that this is actually equal to the integral from 0 to pi by 2 of d theta 1 minus k squared sine squared theta. And so now we are going to show the previous result. So let's start with this integral right over here. So in this integral, I'm going to put k equals b over a. So then this integral will be rewritten as follows. So the a goes outside. Note that we've assumed that a is greater than b is greater than 0, so that this is between 0 and 1. So that's cos squared plus k squared sine squared theta. And I can just write this as 1 minus sine squared, and I can combine these two terms to get 1 minus k squared sine squared theta. And that thing right here, I can rewrite it in the notation of the elliptic integral of the first kind, and it's equal to 1 over a times this over here. And we've shown that in a previous video, but well, that thing right here is called the complementary modulus, and elliptic integrals are a bit like trigonometric functions in that they satisfy certain similar identities. And we in fact have the following transformation for elliptic integral of the first kind. So the elliptic integral of the complementary modulus is equal to 2 over 1 plus the modulus times the elliptic integral of this expression in the modulus. So that this right over here is equal to that. And now, well, that's just 2 over a times 1 plus k of the integral from pi by 2 to 0 of, that's just the definition. And now recall that k is equal to b over a, and so when I replace k equals b over a, this thing right here becomes a plus b, and this one becomes a minus b over a plus b. So that we can rewrite, when you put this inside the radical, this becomes 2 times the integral of a plus b squared minus a minus b squared sine squared theta. And now I'm going to do so here's what I'm going to do. So you can rewrite this thing here as a plus b squared cos squared theta plus a plus b squared sine squared theta by the Pythagorean theorem. And when you add these two and replace, when you add these two, that's equal to 4ab sine squared theta. So this thing under the radical just becomes a plus b squared cos squared theta plus 4ab sine squared theta. And now when you divide this by 2, it becomes 4 inside the radical, which becomes 2 inside that thing right over here, so that's inside the brackets, and this 4 disappears. And that's exactly what we wanted to show, that when you replace a and b by the arithmetic mean and the geometric mean, the result does not change. And now we are only left to prove the very first thing which we wanted to prove, namely that 1 over the arithmetic geometric mean is equal to that integral, where here we replace a and here we replace b. And that's how we are going to do this. So let me erase the board. And I think it's getting a bit messy, so let me clean it even more. Right, so we start with this integral from 0 to pi over 2 of d theta cos squared theta plus b squared sine squared theta And we know that we can replace A by the arithmetic mean and B by the geometric mean. And in that new expression, so it will become A1 plus B1. So A1 is the arithmetic mean and B1 is the geometric mean. We can again replace the means of those, and that becomes A2, B2. And we can go on like that no matter how many times, and the integral will be unchanged. So that will really be an, bn for any n whatsoever. And we can let n tend to infinity. And so when we let n tend to infinity, this integral actually becomes equal to 2 over pi times, well, the limit as n goes to infinity of this sequence is equal to that of this sequence, and we've denoted it by m. So we have m squared cos squared theta plus m squared sine squared theta. And now it's easy, so m squared cos squared theta plus m squared sine squared theta is just m squared, and the root of m squared is just m, and m is a constant, so we can bring it outside. So that's 2m 2 pi of the integral to 2 pi of d theta, and that thing is just equal to pi over 2. So, and when you multiply this, it just becomes equals to, so 2 over pi times 1 over m times pi over 2 is just 1 over m. I think I wrote the m in the numerator before. So here we are, we have our fantastic formula.